Good day to all examiners. Today we are from Group 33. We'll be presenting our plant design project, which is entitled Plant Design for Biogas and Organic Fertilizer Production from Palm Oil Mill Effluent, or as we call it, POM. So my team consists of me, Nora Diba, Chong Yewen, Adriana Zudi, and Jessa Singh, and our project supervisor is Dr. Hilmi. So the outline for today's presentation consists of 7 chapters, which will be presented by all of us. So let's proceed to the first chapter, which consists of background study, problem statement, objective, and scope of work. So the basis of this study is about palm oil industry. Palm oil industry is one of the largest in Southeast Asia, where Malaysia and Indonesia accounts 80% of the global palm oil demand. Palm oil production doubles every 10 years and expected to increase to 78 metric ton in 2030. So this increment is because of the increasing population, which also increases the food demand of the world. So palm oil production is a part of those demands. Next is 1 ton of fresh fruit bunch produces 0.5 to 0.75 ton of POM. So fresh fruit bunch is the unprocessed fruits of palm tree. When processed, it will release what we call POM. So POM consists of mostly water and also solid waste such as fiber and kernel shell. So POM, when treated correctly, it can undergo anaerobic digestion in order to produce biogas, and its digestate can be made into organic fertilizer. So there are 4 problem statements for this project. The first one is the increasing palm oil cultivation also increases palm oil mill effluent. Secondly, POM needs to be treated prior to be released to the environment. This is because it contains high COD and BOD, which may affect the aquatic environment and also its quality. So the third one is the increasing energy demand. So currently our world depends mostly on non-renewable energy such as fossil fuel. So there has to be renewable alternatives, and POM may be one of the alternatives. The fourth one is the unrecovered nutrients from POM, which can be used as organic fertilizer. Why? Because it consists nutrients such as lipids and carbohydrates. But for that, production of organic fertilizer incurs high costs due to the chemicals used for its processing. Next is the objective. There are 2 main objectives. The first one is to design a biogas plant that takes in POM as feedstock and produce biogas and organic fertilizer. And the second one is to conduct the following to evaluate our plant feasibility, which are process optimization, manual mass balance calculation, process simulation, economic evaluation, heat integration, and also hazard study. And our scope of study, there's 6 main scopes, which are literature review, mass balance using Microsoft Excel, simulation using Aspen Plus, heat integration using HIN, hazard study, and also economic evaluation. So that's all for chapter 1. We will proceed with chapter 2 by Jessa.
Hi everyone, my name is Jessa Singh and I will be presenting the literature review conducted for this project. On the global scale, Malaysia is the second largest producer of palm oil behind only Indonesia, who became the largest producer in 2006. Malaysia, however, remains the largest exporter of refined palm oil in the world. As the figure shows, the exports of palm oil has been in tandem with the production rate of palm oil, and this has introduced a booming trend in the Malaysian oil palm industry. Palm oil in itself is a very versatile product and has multiple food and non-food applications. The production of palm oil, however, is far from being eco-friendly, if at all. The process of producing palm oil from fresh fruit bunches produces waste such as palm oil fuel ash, empty fruit bunches, palm oil mill effluent, oil palm frond, and palm kernel shell. For this project, the waste that will be focused on is palm oil mill effluent. So, the effluent is produced as a result of wet milling process, which is widely used to extract palm oil from fresh fruit bunches in Malaysia and Indonesia. During the milling process, there are 3 different stages from which POM is produced. First is sterilization. This process is where fresh fruit bunches are sterilized by utilizing steam at 140 degrees Celsius for 75 to 90 minutes in an autoclave. This process is carried out to deactivate the hydrolytic enzymes that break down oil to free fatty acids besides loosening the fruit from the bunch. This process produces the most wastewater when the steam condenses. Another process from which POM is produced is clarification. This process is carried out to separate water from the oil. Normally, approximately 50% of the produced crude palm oil at this point is made up of water due to the hot steam used to break oil-bearing cells into mesocarp, and this water has to be removed before the crude palm oil can be marketed. Lastly, another process that produces wastewater is hydrocyclic separation. This process separates the palm kernel from its shells based on the difference in specific gravity, and this is where the remaining wastewater is produced. Pomace is a dark brown colored, thick colloidal blend of water, oil, and suspended solids. The table below shows the average values of pomace which is usually released, but their values could deviate significantly depending on the type of process being employed. The following table describes the discharge standard of pomace in Malaysia. Moving on, there are 4 phases in the anaerobic digestion process. Anaerobic digestion is the process used to produce value-added products from pomace by means of digestion by naturally occurring bacteria in an oxygen-devoid environment. Hydrolysis occurs first, and this phase breaks down large molecules into its respective monomers. After hydrolysis, acidogenesis takes place, and this phase further breaks down the monomers into smaller chain molecules which are converted to form acetic acid during acetogenesis. Lastly, methanogenesis is the conversion of acetic acid into the aforementioned methane and carbon dioxide. One of the value-added products that can be produced from anaerobic digestion of pomace is biogas. Biogas consists of mostly methane and carbon dioxide, but also hydrogen sulfide, water, and other trace gases. This value-added product can be used to generate energy due to its high methane content and has the potential to substitute our dependency on fossil fuels which pollute the environment. The figure on the right shows the various uses of biogas, amongst which are in boilers, combined heat and power generation, bio-CNG, as well as internal combustion engines and fuel cells. In some instances, biogas should be more preferred due to its cleaner burn and significantly lower impact on the environment. Another value-added product from the anaerobic decomposition of pomace is organic fertilizer. This product is obtained from the digester that remains upon the completion of digestion. It is rich in nutrients and can be produced via 2 methods, which are co-composting and vermicomposting. While co-composting utilizes aerobic microorganisms and sometimes other biodegradables to reach the optimum carbon to nitrogen ratio, vermicomposting is the natural conversion of biodegradable waste into high-quality fertilizer using earthworms. Organic fertilizers are eco-friendly, cost-efficient, and prevent soil degradation, in addition to being a source of nutrients for crops in comparison to chemical fertilizers. The chart at the top left corner shows our dependency on fossil fuels as a source of energy, with renewable energy sources only accounting for 11% out of 100. This clearly has to change due to the negative effects on the climate caused by decades of utilizing fossil fuels as our main source of energy. Moving on to the bar chart at the bottom right corner, it shows the amount of biogas that is produced by countries in the European Union from landfills, wastewater treatment plants, and other sources such as anaerobic digestion plants, which have been encouraged by their renewable energy policies in addition to economic, environmental, and climate benefits that can be attained. It is projected that biogas production in the EU alone will experience a surge from the current 16.9 million tons per year to 41 million tons per year in 2025. Moving on, the charts describing the domestic and projected installed renewable sources of energy show the percentage produced by different renewable energy sources in Malaysia. The 11th Malaysia Plan, published in June 2015, stated that the government aspired to increase the share of renewable energy in the total energy mix from 1% as of 2014 to 7.8% by 2020, with particular focus being given to biomass and biogas, as the government aims to increase the cumulative total of 28% as of 2014 to 50% come 2020. What this means is that there is a definite demand for biogas in the global market, albeit a small one. Slowly but surely, alternative sources of energy have to be considered and implemented due to the unsustainable effects of continuous use of fossil fuels. As for organic fertilizer, its global demand is projected to increase at an annual growth rate of approximately 7% until 2024, with a market projected to increase from $3.9 billion in 2016 to $6.3 billion in 2024. This growth can be attributed to disseminating and acquiring knowledge, overall effectiveness of organic fertilizers, stringent government policies in terms of pollutant emissions, as well as awareness of the negative side effects of chemical fertilizers. The table below shows the global demand for organic fertilizers from 2015 to 2019, with a forecast for 2020 inclusive of an average annual growth of 1.9%. From the table, it is evident that the global demand for organic fertilizers is increasing steadily year after year and will continue to do so as long as sustainable practice is continued. For site selection, 3 sites were considered prior to making a final decision based on an evaluation. These sites were located at Tamerloh in Pahang, at Kulai in Johor, and at Kinabatangan in Sabah. An evaluation of these sites was carried out by using the 12 factors that affect the plant's location and layout. The evaluation consisted of assessing factors that would affect the operation of the plant directly, and we came to the conclusion that the site in Kulai, Johor was the best as it obtained the highest overall score in the evaluation. That's all for the literature review of the project. I would now like to pass it on to my fellow groupmate Chong Evan to explain the conceptual process design and economic analysis.
Thank you, Jessa, for the clear explanations on the literature review just now. My name is Chong Evan, with metric ID 24060. The topics I'm going to talk about are conceptual process design and economic analysis, which fall under Chapter 3. The aim of conceptual process design is to evaluate few alternative processes and select the best process among them for the design. The first part of the conceptual process design is the preliminary reactor optimization. Several evaluations have been considered to optimize the reactor conversion, yield, and selectivity with the economic potential analysis on the reactor cost model. There are 4 different methods that are currently available, which are evaporation method, anaerobic digestion process, membrane treatment system, and aerobic treatment. This table tabulates the advantages and disadvantages for all the 4 methods. For comparison in terms of energy, anaerobic digestion has a bigger extensive as compared to other methods, has low energy consumption because no energy is required for aeration in anaerobic digestion. Indeed, anaerobic digestion is referred to the interactions among bacteria in the absence of oxygen. Moreover, anaerobic treatment will generate biogas such as methane and carbon dioxide as valuable products which can be captured and commercialized. For other methods like aerobic process, a huge amount of sludge is generated along with treated wastewater, even though shorter retention time is needed. The greatest weakness for the membrane and the evaporation treatment method are costly membrane and high energy consumption respectively. Other than that, with respect to the capital cost, previous studies have indicated that the overall capital cost of employing the anaerobic treatment is considered low. So therefore, anaerobic digestion process has been proposed for this project. However, anaerobic treatment demonstrates 2 major drawbacks, which are long retention time and long startup period. But no worries, these 2 issues can be solved by using granulated seed sludge to shorten the lengthy startup period, and the other method is by using high-rate anaerobic bioreactors to reduce the retention time. This figure shows the flow diagram of the anaerobic digestion process. The hydrolysis, acidogenesis, and the methanogenesis are the 4 major steps involved in anaerobic digestion process. This was mentioned by Nananda Jessa in detail in his previous slides, so I won't further touch on this. Next, there are several key factors that affecting the anaerobic digestion, such as temperature, hydraulic retention time, organic loading rate, and pH. For the temperature, it can be divided into mesophilic and thermophilic. Mesophilic is the condition where the temperature is ranged from 25 to 40 degrees Celsius, whereas for thermophilic condition, the temperature used is from 50 to 60 degrees Celsius. Thermophilic condition result in better mass transfer and higher digestion rate. Too low hydraulic retention time will result in incomplete degradation process or washout of bacteria. Higher organic loading rate provides better removal efficiency of COD. For production of biogas, optimum pH needed to be at range of 6.8 to 7.6. Next is the anaerobic reactor selection. There are several types of anaerobic digesters for treating the pond wastewater. The example of bioreactors are the CSTR, expanded granulated sludge bag, EGSB, anaerobic fluidized bag reactors, AFBR, and so on. This table tabulates the advantages and disadvantages of different types of designs for anaerobic treatment methods. The criteria for the selection of reactor is based on the operating cost, simplicity, and efficiency. With regards to this, CSTR is chosen as the optimum and best fitted reactor due to several reasons, such as it is simple to operate, continuous mixing causes a good contact between the foam and microorganisms, low operating and maintenance costs, and most importantly, it is suitable to use for industrial scale of the treatment of foam. Moving on, two-stage anaerobic digestion. Various efforts have been put forth to improve the techno-economic feasibility of the anaerobic digestion process. These include two-stage anaerobic digestion system, where splitting the 4 phases of anaerobic digestion in order to allow optimum conditions for microbial growth, which in turn increase the biogas production. Based on the previous literature, the biogas yield is increased by up to 30% compared to a single-stage system. For the attempt of reducing hydraulic retention time, many studies have been done on the two-stage anaerobic digestion process, namely acidogenesis and methanogenesis stage. Next, I would like to talk about the pre-treatment selections to enhance the biogas yield. Fresh foam is required to be treated before feeding to the reactor to ensure shorter processing time. Besides, when the treated foam is more consumed by microbial groups, thus higher rate of digestion during anaerobic digestion can be achieved, which increase the biogas production. There are two ways to pre-treat the foam. The first one is the addition of ash. Ash can be known as a waste product from the boiler. The main functions of adding ash into the foam is to increase the volatile solid degradation rate and increase the biogas yield, act as a coenzyme to decrease the acidity of the foam feed and help to eliminate oil, grease, and heavy metals. The second method is through co-digestion process by adding the anti-fruit branches, shown here. Co-digestion is the utilization of two or more ways where higher production rate of biogas can be achieved compared to mono-digestion of substrate. Co-digestion process is a cost-effective way to treat the organic waste. Anti-fruit branches 60 to 70% of moisture content and higher organic matter content are generated as a byproduct from processing of the fresh fruit branches in palm oil mill industry. In this process, the ratio of EFP to foam used is 0.4 to 1. Moving on is the biogas cleaning technology selection. The biogas captured from anaerobic digestion of foam contains some impurities, especially hydrogen sulfide, that are required to be removed. The removal of H2S from the biogas is a very important step because H2S is corrosive to the equipment such as storage tanks, pipelines, compressors, engines, and so on. As illustrated in the figure here, there are 6 purification technologies available such as water scrubbing, cryogenic separation, physical adsorption, chemical adsorption, pressure swing adsorption, and membrane technology. According to this table, H2S is required to be eliminated for cooking gas application, as the H2S removal requirement for boiler to be directly used is less than 1000 ppm. Further purification of biogas is not needed after removing the H2S for cooking gas and industrial heating applications. Next is the selection of H2S purification method. The criteria of selecting the best fitted H2S removal technique includes the composition, volume of biogas to be treated, cost, and gas final use. These tables summarizes the advantages and disadvantages and also the features of all the purification technologies. As compared, the best fitted H2S removal technology is water scrubbing. Due to low operating cost, simplicity of operation, high methane purity, and low methane loss, water scrubbing can eliminate the acid gas contaminants such as carbon dioxide and H2S simultaneously and separate them out by using the air stripping tower. Moving on to process flow sheeting. This figure summarizes the overall process of the zero discharge foam treated treatment process in block flow diagram. There are overall 4 processing units included in the system. The first one is the pond pre-treatment. Second, anaerobic digestion of the pond. Third is the biogas cleaning for cooking gas and boiler utilizations. And the last one is the digestive treatment for biofertilizer production. Pre-treatment process refers to the screening process to protect the downstream equipment against the impairment, prevent reductions in efficiency with plant operations, and avoid interference in the whole system. For the biological treatment, 2 anaerobic digesters are arranged in series to digest and degrade the organic matters effectively. For H2S separation, water scrubber is used to remove the corrosive H2S. Biogas dehumidifier aims to minimize the moisture content in the biogas before it can be used in gas engines. Biogas produced with an anaerobic digestion process is used to fuel a boiler and for cooking gas utilization. Half of the purified biogas is channeled to the bottling plant and half of them is used for boiler in the palm oil mill. The next one is the overall process flow sheet selections. For the overall process flow sheet selection, there are 2 options in searching the most feasible and profitable process flow for the biogas and biofertilizer production from pond. For the option 1, there are multiple pre-treatment used to achieve the perfect fit conditions. The dissolved air flotation tank is utilized to produce thicker sludge where it is the process of solid liquid separation using air bubble flotation. In option 1, the product is used to generate electricity. However, due to high energy required and the distance from the plant to the vendor, extra capital costs in installing grid lines and transformers are needed. Meanwhile, for option 2, the core feed to be added alongside pond and empty fruit bunches is ash. Addition of ash is proven to increase the biogas production of biogas. In option 2, the product of biogas is partly used to power out the boiler to replace part of the biomass fuel. Therefore, option 2 is accepted as a better process design compared to option 1 due to less complexity of pre-treatment process and the end product. Option 1 produces liquid fertilizer, whereas option 2 utilizes the liquid for the sludge for recovery of liquid.
Next, we'll proceed with the manual mass balance. So we conduct the manual mass balance calculation using Microsoft Excel for each process unit. For this presentation, we're only looking at 3 main process units, and the first one is anaerobic digester. So for anaerobic digester, it's where the reactions occurs, and there are 5 main reactions that we consider for our mass balance. And these reactions are reactions for carbohydrate, protein, and lipid. And as you can see in the diagram, stream 8 is the biogas pathway, while stream 9 is the organic fertilizer pathway. And for our calculation, we assume a conversion of 90%, and also we assume reactor efficiency of 90%. Next is water scrubber, where hydrogen sulfide is removed. We assume 97% hydrogen sulfide is absorbed, and the rest is reduced with methane. And for our product, methane produced is 563 kg per hour, while methane produced from simulation is 339.3 kg per hour, and the percentage difference is almost 40%. Next is sedimentation tank, where water and the remaining digestate for organic fertilizer is separated. So as we can see from manual calculation, we got around 41,000 kg per hour, while from simulation we gained 51,000 kg per hour, and the percentage difference is 23.7%. Next, we will proceed with economic evaluation. So in order to calculate our annual operating revenue, we consider 2 items. The first one is for biogas generation, and the second one is for compost. And for each calculation, we consider the cost of development or implementation, the estimated annual operation, and also maintenance cost. So from these values, we're able to calculate our estimated annual revenue. So the total annual revenue is at 8.4 million, while the payback period gain after all the calculations is 2.29 years. So that's all for this chapter. We will proceed to the next chapter, which is chapter 4 by Adriana.
My name is Adriana Zudi binti Lufia Mezudi and my ID is 23704, and for today I will explain about the heat integration and also the process flow diagram. So heat integration is a process to utilize the heat that is produced from the process to be integrated into the heat exchanger. So this will reduce any utilities consumption and also the reduce operational and also the capital cost of the process. So to do this, we have an approach of pinch analysis, which is a tool that is used to design the heat recovery network. So this recovery network will be means to achieve the minimum energy target for the design, which will have the minimum heating and also cooling requirement, and also minimum number of heat exchanger and minimum heat exchanger network area. So to approach this is by using problem table algorithm or PTA. A method to do PTA is by having data extraction, temperature shifting, finding CPNet, interval temperature, and also the heat duty, and the construction of cascade diagram. So firstly is about data extraction. So from the process, there are three streams that can be identified to be integrated, which is from the outlet of the compressor to the scrubber, and then from the sludge to separator, and from the mixing tank to the reactor. So there are two hot streams and also one cold stream. Next is we have the minimum temperature approach of 10 degrees Celsius, and this temperature shifting and also CPNet is being used to construct the cascade diagram where the duty can be found using Q equal to M Cp delta T. So by using the hint software, we can obtain this cascade diagram where the information can be extracted, which is at the enthalpy of 0, we can get the pinch temperature, which is 50 degrees Celsius, and also the minimum heating utilities and also minimum cooling utilities. So from this information, we can construct a heat exchanger network, or we can call this as maximum energy recovery heat exchanger network, or MER. So for this heat exchanger network, we use the concept of for above, this is above pinch and also this is a below pinch, and we must construction is depends on the rules where for the above pinch the CPC must be less than CPH, and for the below pinch the CPC must be larger than the CPH. So from this information, we have constructed the maximum energy recovery, and it is found out there is one splitting of the stream, and there is 3 heat exchangers, 1 heater, and 2 coolers. So before we did the heat integration, we can see that the utilities of the process of the heat exchanging that we use before heat integration is larger, and we can see the difference after we had done the maximum energy recovery. We can see that there is difference in terms of the utilities used. And to further optimize this heat exchanger network, we can use the energy relaxation, which will allow reduction in the capital cost by removing small or any uneconomic exchanger and allowing small penalty in the energy usage. So the advantage of this optimization is to reduce the heat exchanger area and also to reduce the number of heat exchanger and further reduce the complexity, which is means by less splitting of the stream. So this is the loop and path, which is a method to do the optimization. So this is the path and loop that we had found in the heat exchanger network. So both are being used. For example, we can see on loop 1, this is the duty, this is the loop where the smallest duty is at this stream of this exchanger of 3 with 13.1407. So this is considered as small heat exchanger. So this exchanger will be removed to optimize the exchanger unit. So after that, we can find maybe some violation in the temperature, so we will use a bath. So the final design of the heat exchanger network is as this diagram, where stream 6 and 1 is the hot stream and stream 2 is the cold stream, and the number of exchangers is reduced to 2 and only one cooler and one heater. So this is the comparison table that we can see, where before the heat integration the number of heater is remain, where the number of cooler is reduced to 1 after we had done the optimization, and the number of exchanger is reduced from 3 to 2, and the number of split also reduced from 1 to 0. And we can see that by using the heat integration, we can reduce the amount of utilities that is being used for the process, where it from, for example, in hot utilities we have 1895, we reduce into 443. Although after optimization it has slightly higher duty, it means that but it still can reduce the capital cost of the exchanges, because we have removed any uneconomic exchanges. So I will next go to the process flow diagram. So this is the process flow diagram for our POM production from where we have biogas production from the POM. So this is the description of the overall process. So I will go one by one, which is firstly is about the pre-treatment. Pre-treatment is to treat the POM, where at first we have the mesh screen. We will separate any coarse or any fine solid contaminants, and then it will go to oil separation tank. We'll collect slash oil, and then the POM will enter the mixing tank, where we will add the co-feed of ash and also empty fruit bunch into the mixing tank, and also water. The co-feed act as the substrate for the co-digestion. So after mixing, we will go to the anaerobic digestion process. So for anaerobic digestion process, we have two reactors of CSTR and we place it in series. And the condition for our reactor is in thermophilic condition, where the temperature is at 55 degrees Celsius, and hydraulic retention time of the effluent is around 7 to 10 days. So the product from this digestion is biogas and also digestate. So the digestate will be used to obtain organic fertilizer. So the biogas that is produced may contain some contaminants. So what we do is we have water scrubber. So the biogas that is produced is compressed to 10 bars and enter the water scrubber, where we use the water to remove the contaminant, so that the biogas that is produced on top of the water scrubber is a high purity biogas, and any contaminant will be removed in the bottom part of the water scrubber, where it will contain hydrogen sulfide and some carbon dioxide. So the high purity biogas is then being insert into the biogas dehumidifier, where it will remove some of the humidity inside the biogas, because it can further inhibit the condensation that can occur inside the biogas and further optimize the combustion process in the engine, which will minimize the acid formation. The acid can be formed when the water reacts with any oxygen or hydrogen sulfide. So this biogas will have overall humidity of less than 80%, which means it will have high quality and well suited for engine use. So the product of biomethane that we obtain will be used for cooking gas and boiler, where half of it will be sent to the bottling plant of biogas, and also the half of it will be used in boiler for the palm oil mill. So next is for the digestate that is obtained from the reactor. It will be thickened by sedimenting in for a few days and to be a concentrated sludge, and this concentrated sludge will be separated from its liquid. So the solid will be the biofertilizer, and the liquid will be recycled back to the mixer as the makeup water. So that is all for the overall process description. So I will pass to the next presenter. Thank you.
Thank you, Adriana, for the presentations on heat integration. Now we enter to the next chapter, chapter 5, which is the process control and implementation. For anaerobic digestion process, The process control and implementation are implemented for monitoring and controlling the process effectively in order to improve the biogas plant performance. The process flow of the pond to biogas can be monitored at different process stages, from the initial feed supply chain to the final stage of biogas cleaning and the biofertilizer production. Especially in the anaerobic digestion, there are specified environmental conditions for active microorganisms growth in order to ensure an effective conversion of organic materials into biogas, which the temperature and pH become the key process variables. Before we started to construct the P and ID diagram, we need to identify the control objectives and also the process variables. This table tabulates the control objectives and the process variables for each unit operation. Let's take a look at the first unit operation, which is the mixing tank. The control objective of the mixing tank is the ratio of the empty fruit bunches, ash, foam are maintained to achieve the desired conversions and yield in the reactor. The ash to foam ratio should be maintained at 2 grams of ash and 170 milliliters of foam. And the ESP to foam ratio should be maintained at 0.4 to 1. The flow from the feed stream to the mixer is controlled to a particular set point to ensure proper mixing composition of the components entering the anaerobic digester. Also, the liquid level of the mixing tank is monitored to avoid overflow. The next unit operation is a heater. The heater is used for heating the inner stream to the first anaerobic digester to achieve the thermophilic condition, which is 55 degrees Celsius. The control objective is to maintain the reaction temperature of the anaerobic digester at 55 degrees Celsius. The exit temperature of the process stream from the heater is manipulated by manipulating the heating medium flow rate. Next is the cooler. Cooler is used for cooling the inlet stream to the water scrubber to prevent overheating and to provide suitable operating temperature conditions for water scrubbing process. The control objective is to maintain the temperature of the inner stream to the water scrubber at 40 degrees Celsius. The exit temperature of the process stream is controlled by manipulating the flow rate of the cooling water. Next is the anaerobic digester, which is also called the CSTR. There are 4 process variables to be controlled in CSTR. The first one is temperature. Second one is the pressure, fluid level, and also the pH. The optimal temperature for thermophilic conditions is 55 degrees Celsius, while the optimal pH for anaerobic digestion is 6.5 to 7.5. The level of the fluid should be maintained to ensure the optimal fluid level in the reactor is achieved. And also, the pressure inside the reactor has to be controlled to prevent overpressure. The next one is the compressor. The control objective for the compressor is to bring the pressure of the stream to 10 bar before entering the water scrubber. The next is the biogas storage tank. The internal pressure of the storage tank is monitored to avoid overpressure. The last unit operation, the pump storage tank, with the control objective to control the liquid level inside the tank to prevent overflow. After identifying all the control objectives and the process variables for each unit operation, with reference to the process flow diagram drawn in Chapter 3, the piping and instrumentation diagram for the biogas and biofertilizer production plant is illustrated in this figure. The breakdown of each process unit will be presented in the next few slides. We have a better understanding on how the process control is done. First of all, we have part of this P&ID diagram starting from the pump storage tank to the mixing tank. The focus on this part is on the mixing tank. And we have 3 inlets flowing into the mixing tank, which are foam, ash, and also the anti-fruit bunch. The flow rate of these 3 are the manipulated variable, and the control variable is the liquid level inside the mixing tank. The type of controller is feedback controller, and also the type of instrument used here are the first one, magnetic flow meter, which is used to measure the flow rate of the flow. Secondly is the level meter, which is used to indicate the liquid level inside the tank. We also have some control valve here. This is called the gate valve, and also this is called the Dyson valve. These valves are used to manipulate the flow rate of these reactants. This valve can be adjusted by the operator manually. Next, after exiting the mixing tank, the stream is subjected to the heater before entering the anaerobic digester. So, to explain the principle of the process unit, we take the example of the heater here. The control variable for the heater is the stream acid, the temperature of the acid stream of the heater. So the value of this control variable comes to the temperature transmitter, and this transmitter will convert it to an appropriate signal, which is the representation of that control variable value. So after converting to the signal, it's passed to the controller, and the controller will send a pneumatic signal to the control valve. This control valve will react to the controller and control the flow rate of the low pressure steam will be adjusted by this valve. So this principle is applied to other process units. For the anaerobic digester, there are three control variables, which are the liquid level in the reactor, the pH of the reacting medium, and also the pressure in the reactor. The control units for the first digester is almost similar to the second digester. We have this PRV, pressure relief valve, which is used to control the internal pressure in the tank. We also have this for the process unit to control the pH of inside this reacting medium by manipulating the flow rate of the ash into the mixer. Lastly, we have, after exiting the second digester, the second CSTR, the stream is subjected to the compressor before entering the water scrubber, because we want the pressure of the stream to be increased to 10 bar. So in this diagram, the type of equipment that needs to be controlled are compressor, cooler, water scrubber, and the biogas storage tank here. So for the compressor, the control variable will be the pressure of the outlet stream from the compressor, and the manipulated variable is the rotational speed of the blade in the compressor. For the cooler, the control variable is the temperature in the water scrubber, and the manipulator would be the cool water flow rate here. And for the water scrubber, there are three control variables related to this. The first one is the liquid level, and the manipulator would be the outlet flow rate of the liquid from the scrubber. The second is the inner flow rate. Inner water flow rate, the manipulator is the amount of water supplied here. And the last one is the pressure in the water scrubber, and the manipulator would be the inlet pressure. The last one is the biogas storage tank. The control variable of this is the pressure inside the tank, and the manipulated variable is the biogas inlet flow rate. So that's all. That's all for my chapter. I would like to bring out the next speaker, Cesar, to talk about his chapter, Hands Off.
Hi everyone, I'll be presenting Chapter 6, Plant Layout and Hazard and Operability Studies. Hazards are potential sources that may cause harm to those working in the vicinity. The hazards can be caused by slight deviations from the operational parameters set for a specific process, and as such, it is very important that these hazards are identified and mitigated to prevent anything untoward from happening. This is where HAZOP plays a very important role. HAZOP stands for Hazard and Operability Studies, and it is conducted comprehensively on equipment to examine the design for operation of a process in order to study the hazards posed by potential deviations as well as any operability problems. To ensure the HAZOP study carried out is efficient and effective, guidewords are used in HAZOP. These guidewords help stimulate the imagination to better identify potential hazards and operability problems. Displayed below are examples of guidewords that are used in HAZOP studies, as well as various parameters of which a select few were studied in this project. For this project, HAZOP was carried out at 4 nodes, and these 4 nodes are anaerobic digesters, hydrogen sulfide scrubber, biogas dehumidifier, and the stripper. So below is an example of a hazard and operability study for node 1, the anaerobic digester. The parameter being studied is float, and the guidewords used are no, less, and more, which are meant to indicate no flow, less flow, and more flow. The possible causes for no flow into the digester could be due to pipe blockage, control valve failure, or pump failure. The consequences for these causes are there will be no feedstock going into the digester for biogas production, which will further lead to no biogas yield. In order to mitigate this, flow meters should be installed along with high pressure and low flow alarms. Besides that, regular maintenance should be carried out for pipes and control valves. Similar as to how HAZOP study was carried out for node 1 for the flow parameter, HAZOP was carried out for the remaining nodes with parameters encompassing pressure, temperature, and agitation. Attached is the conceptual design of our plant layout. It is inclusive of process and non-process areas which are essential for day-to-day operations in addition to an area for future expansion should the need arise. Among the non-process areas within the plant are as stated below. Each of these areas have their own vital importance to the day-to-day operations of the plant. These areas are meant to ensure smooth operation and safety of personnel on site. Among the process areas within the plant are as stated below. The viability of these areas is directly linked to the ability of the plant to operate as designed. These areas comprise storage areas for raw materials and products, laboratory for testing, utilities for power, control rooms, as well as the production area itself. That is all from me for the HAZOP and plant layout for our project. I would now like to call upon my fellow groupmate to conclude our presentation.
So here we are at the last part of our presentation, which is the conclusion. So our team is able to construct a plant design which takes in pome, ash, and an empty fruit bunch as feedstock. And from this feedstock, we are able to produce biogas and organic fertilizer. Our plant is expected to be in Kulai Johor. In regards to our process flow, we are able to take in 126,000 tons of pome per year. And the pome undergoes 4 main processes. The first one is screening, where it is a pre-treatment process to remove oil and grease. Second one is anaerobic digestion, where we use continuous third tank reactor for reactions to happen. The third one is scrubber, where hydrogen sulfide is removed. And the fourth one is sedimentation tank, where it is used to separate water and the remaining digestate for organic fertilizer. In terms of plant feasibility, there are several studies being conducted. So the first one is heat integration, where we use HIM software to utilize heat from process. The second one is HAZOP study, where we examine and inspect design operation in terms of its hazards. The third one is process control, which is used to maintain optimum process by integrating heat, temperature, and pressure control. And the last one is economic evaluation, where we gain our payback period of 2.29 years. So that's all from us. We may proceed with question and answer session from the examiners. Thank you.